Hello everyone, and thank you for joining us. I'm Niall Buchanan with Broadcom, and I'd like to welcome you to our session today on the topic of security digital certificates on zOS. There are a lot of new and exciting advancements taking place in the space, and the focus of our session is what certificates are and how they are managed in zOS. If you have any questions during the webcast, please feel free to submit those through the chat window, and we'll be having a live Q&A at the end of the session. And don't forget to fill in your feedback form and contribute to the charity. And with that, I'd like to turn things over to our speakers, Jameson and Seamus from Broadcom.
Hey everyone, thanks for joining our presentation today. I'm Seamus Hayes and I'm joined by Jameson Walker, who'll be giving the second half of the presentation. So this is just a really pretty much basic presentation about certificates. In the first half, I'll just explain to you what a certificate is, kind of the underlying knowledge you need to know to understand how they work. And then Jameson will give you some more practical knowledge on how they're used on zOS. So let's jump right into it. So let's start at the very basics. What even is a certificate? I like to think of it like a digital ID card. And really what it is, it's just a file that contains a cryptographic key, which we'll go into later what that is, and then details about whichever person or organization owns that key, and then a signature verifying the validity of that certificate. So we'll go into how all of that works and what all of that is as this presentation goes on. Using certificates are used in things like TLS communication, or if you're on the web browsing HTTPS, you're using certificates even if you don't know it. And certificates provide for you four main benefits. Those are authentication, non-repudiation, integrity, and privacy. Authentication means that the receiver has reason to believe that a specific person sent that message. Non-repudiation means that the sender can't deny that they were the person that sent that message. Integrity ensures that the message was not changed at all during transit, so it's the same as the author originally sent. And then privacy, meaning only the intended recipients can decipher the message. So in order to really understand certificates, we have to go over some basics of cryptography. And the first type of cryptography we'll be learning about is called asymmetric encryption. And this is the first appearance of those cryptographic keys I was talking about. And really what those are, they're just numbers that are used as inputs for an encryption or decryption algorithm. So along with the key, you input to the encryption algorithm whatever text or data you want to encrypt. And then the result of that is the cipher or the encrypted data. And in the case of symmetric encryption, what we're looking at now, the same key you use to encrypt the data, you pass into the decryption algorithm to decrypt the data along with the encrypted data. And the result of that is just the original data that was encrypted, right? So you're using the same key to both encrypt and decrypt the data, and that's symmetric encryption. So let's look at an example. We have Alice and we have Bob. Alice has got a sensitive document that she'd like to send to Bob. So she's going to use symmetric encryption, and she's going to use the key she has to encrypt that document. She's then going to send the encrypted document over to Bob. And now Bob needs to know the key Alice used to encrypt the document in order to decrypt the document. So he asks, what's the passphrase? What's the key? So Alice sends the passphrase over to Bob, or the key over to Bob. But the problem is that she's sending the key in plain text, so anyone can intercept that key and then read all the communications between Bob and Alice, even though it was encrypted. So you might say, why doesn't Alice just encrypt the key before she sends it to Bob? Well, then we just end up with the same problem. How will Bob know how to decrypt the key? He'll have to ask Alice for another key, right? So how can we securely share keys between each other? And that brings us to asymmetric encryption. In this case, instead of using one key to encrypt and decrypt the data, there's now two keys, right? There's the public key and the secret key. The public key is used to encrypt the data, and then the secret key, also called the private key, is used to decrypt the data. And these keys come together in what's called a key pair, and only keys from the same pair can encrypt and decrypt the data. So if I use a public key from one key pair and then a secret key from a different key pair and try to encrypt and decrypt data with those keys, you'll just get garbage. So it has to be keys from the same pair. So let's look at an example here. We have Alice and Bob again, same scenario. Alice wants to send Bob a document. But in this case, they both generate their own key pairs using what's called RSA algorithm. That's unimportant. It's just an example of an algorithm to generate a key pair. But in this case, Alice and Bob now each have their own key pair. As the name suggests, the public key can be shared with anybody you want. It can be disseminated widely. You can put it on a billboard outside your house. You can put an ad on the TV. It doesn't matter who knows your public key, right? So Alice and Bob can just mail each other the public key. It doesn't matter if the hacker intercepts that communication. The public key can be known to anybody. So now Alice is in possession of Bob's public key, and then Bob is in possession of Alice's public key, along with their own key pairs. So now Alice again wants to send a document to Bob. And here's the important part. Remember I said you can only encrypt and decrypt with keys from the same pair. So in this case, Alice wants to send a document to Bob, which means she wants Bob to be able to decrypt that document. Decrypting uses the private key, and Bob is the only person in possession of Bob's private key. So that means Alice has to use Bob's public key to encrypt the document, because then when he receives the encrypted version of the document, he has his own private key that he can then decrypt and read the document with. If this encrypted version of the document gets into anybody else's hands, since they don't have Bob's private key, only Bob has his private key, they'll be unable to decrypt the document and read the message. Right, so Alice sends it over to Bob. Bob uses his own private key, and he can read the message. Cool. And this whole scheme relies on that the private key is kept secure. If your private key is leaked or shared with anybody else, your whole key pair is compromised, and you have to generate a new key pair, and you have to make sure your private key is secure. So just to recap, that was called asymmetric cryptography, also known as public key cryptography. And remember, that uses two keys. One's called the public key, and the other is the private key or the secret key. The public key can be disseminated widely. The secret key you have to keep to yourself. The public key is used to encrypt a message, and then only that corresponding private key can be used to decrypt the message. And just remember, keys are simply numbers that are inputs to encryption and decryption algorithms. That's all they are. It's just a number. And this is what a key might look like if you print one out. This is just an encoding of a number. Right, that's all it is, nothing scary. And the final thing we'll have to learn about is hashing. This is pretty simple. Hashing is just a one-way function that converts any form of data into a unique sequence of bytes. So the input that you hash can be of any size and any type, it doesn't matter. At the end of the day, it's all just ones and zeros. And regardless of the size of the input, your output hash will always be the same size. Again, hashing is a one-way function, meaning that just by inspecting the output, you can't determine what was input. And the same input will always produce the same output. There's no element of randomness at all. And then even the tiniest change in the input to a hash will cause a completely different output. And we'll see some examples now. So on the left-hand side, we have inputs to our hash functions. On the right-hand side, it's the digest or the hash. And then in the middle, we're just performing the hash. So as you can see, regardless of the size of the input, our digest or hash is always the same size. Between the second and third box, and it might be difficult to see, but the V in over was changed to a U, so it's a single character change. And despite that single character change, if you inspect the hashes, you can see they're completely different, even though the change is really small. Same story for these next couple boxes, just small changes, character deletions, switching characters around. No matter what the change is, you're going to get a completely different hash. So that's what hashing is. At this point, I don't know if we can stop for questions in the middle of the presentation, but if anybody has got any questions about symmetric cryptography, asymmetric cryptography, or hashing, I can field those now. Otherwise, at the end, will work as well.
No questions coming in over chat at the moment.
All right. Yeah, if you think of one and have it at the end, that's fine. So yeah, now we understand the basic knowledge. How does this all come together? How's it used in certificates? How's it used in the real world? Well, the first thing you might have heard of is called a digital signature. So just like a real signature, yeah, I mean, it's good to think of it just like a real signature, right? It does not encrypt the message itself, but it simply attaches an identity to the message. So just like if I were to hand you a signed letter, anyone that comes into possession of that letter can read the letter, but they see the signature at the bottom and they say, oh, I recognize this is Seamus's signature, so I have reason to believe that Seamus wrote this letter, right? So that's what a digital signature is. It's the same thing. It doesn't encrypt the data, but it's a way to digitally attach a signature to a document or whatever data that gives people reason to believe that a certain person was the author of that document. And then it also gives them a way to check that that document wasn't changed by anyone in the meantime, right? It's the same as originally signed by the author. So this fulfills three of the purposes of certificates: the authentication, non-repudiation, and integrity. The one it does not fulfill is the privacy, because again, it does not encrypt the message at all. It just gives people a way to verify who authored the message and that the message is the original. Okay, so just a quick note, encryption versus signing. When you're encrypting a message, remember you use their public key to encrypt it because they use their own private key to decrypt the message, as they're the only person that has their own private key. When signing, you want to use your own private key to sign a message, and then other people use your public key to verify that that message was signed by your private key. And remember, because I'm the only person that owns my private key, if someone else tries to verify my signature with any other public key besides my own, then it won't work out and they'll say, okay, this message really wasn't authored by Seamus. So as an example, this is how the signing and the verifying works. Pretend again, this is Alice here as the signer, and she's sending something over to Bob, and Bob needs to verify that Alice really created that message, right? So how it's going to work is Alice is going to have the original message or data that she wants to send and sign. And what she's going to do is she's going to compute a hash from that data, right? So now she has a hash of her original data. And what she's going to do is she's going to use her own private key, because remember, she's signing the data. She's going to use her own private key to encrypt the hash and end up with an encrypted version of the hash. So now the end result of this whole process is the original document unencrypted, because remember, signing does not encrypt the data. So the original plain text document plus an encrypted version of the hash that Alice calculated. So she's going to send this over to the network to whoever wants to verify, in this case, Bob. And so Bob, he's going to get the original document, and then he's going to have an encrypted version of the hash. What Bob's going to do is he's going to take the original document and compute the hash himself. So now he's going to have a hash that he created himself. Then he's going to take this encrypted hash that Alice sent him, and he's going to use Alice's public key to decrypt the hash. So now he'll have two hashes, the one he computed himself, and then the hash Alice sent him. What he wants to do is now compare these hashes and make sure they're the same. If the hashes are the same, then he can be reasonably sure that Alice sent the message, that the data in the message wasn't changed between the time Alice signed it and he received it. And yeah, so he can be sure Alice sent this to me, and this is the message she actually sent. If these hashes do not match, it can mean a couple of things. It could mean Alice did send the message, but somebody replaced the message afterwards. So the message that Alice signed and the message she received wasn't the same. Or it could mean somebody besides Alice authored that message completely, and it's just not Alice, right? So if these hashes aren't equal, he can't tell exactly what the problem is, but he knows something's wrong, and he knows that he can't trust the message, right? So there is one problem with this whole scheme, and it's kind of hard to pick up on, but I think you'll notice it. If we go back a slide, the problem comes into the public key that the verifier uses. It makes sense if this is Alice and Bob, like two people talking to each other. If I'm trying to verify the message, I can call up Alice and I can say, hey, Alice, I have this public key. Does this public key actually belong to you? And she can say yes or no, right? But if this is two pieces of software communicating, like a server and your laptop or whatever else, they can't call each other up and say, hey, is this really your public key? So where are they getting these public keys from? If the person just sends you their public key and says, hey, I'm Seamus, here's my public key, now you can trust me. Well, I could be lying, right? I could be a hacker, and I could be contacting you and saying, hey, I'm actually Seamus, here's my public key. So you'll believe that you have a public key that belongs to Seamus, even though it actually belongs to the hacker. and you might be communicating with me, you might be verifying the signature, and you'll be reasonably sure that everything's true because you're going through this whole process of signing the documents. But the problem is you weren't using the public key that actually belongs to me, and the whole time you were communicating with an imposter, right? So how can we fix this problem? How can we be more confident of a sender's identity? And that's where we come first full circle back into digital certificates. So at the beginning of the presentation, I said a certificate is a document that has a cryptographic key, the identity of who owns that key, and then a signature by a third party that verifies the validity of that information, right? So now we should understand what the key is, right? The key is the public key that other people can use to confirm your identity and talk to you. So you want to make sure that other people have your real public key, or not talking to an imposter or have the wrong key, right? So that's what a digital certificate is for. It says, here's my key, here's the person who owns it, or here's the company who owns it, and it was issued by this third party, which is called a certificate authority, which are these trusted companies who their whole business model relies on them being able to verify a key and identity and to associate them together, right? So if they start issuing certificates that have fraudulent keys or fraudulent identities, their whole business will go down the drain. People won't trust them anymore, right? So they have a lot of incentive to make sure that when they issue a company or a person a certificate, that person or company is who they say they are, and that key actually belongs to them, right? So that third party is called the certificate authority. And this whole scheme kind of relies on trust that the certificate authorities went through the proper measures of verifying identities and verifying keys, right? So certificate authorities, the top 5 nowadays are IdenTrust, Komodo, DigiCert, GoDaddy, GlobalSign. Of course, there's more, but like I said, they're responsible when somebody applies for a certificate by creating what's called a certificate signing request, or a CSR. They're responsible for validating all of that information, making sure it's true, nothing's fraudulent, and then they can issue a certificate. An important thing to note is pretty much all your web browsers or any application that's web connected comes pre-installed with the certificates of these major certificate authorities, just so it never has to go anywhere to ask for what the certificate authority's key is, because that would be an opportunity for somebody to give them a false key. So by everything coming pre-installed with these certificate authority keys, that gives us like a base layer of things we can trust and build everything off of. So this is a certificate signing request. If you've ever tried to procure a certificate, or if you will in the future, you'll have to create one of these. It's pretty simple. Pretty much it just contains your key and then all of your information, whether it's your company or your personal information. And this is what the certificate authority looks at to verify your identity and key, and then to eventually generate a certificate for you. So when you have a certificate, remember, it's just like any other data, like we were looking at earlier when you're signing, except for this. In this case, the data is a key and an identity. But again, you send your certificate to anyone who you want to share your public key with. And then using the public key of the certificate authorities that come pre-installed on all their computers and software, they can validate that, hey, this certificate was actually signed by Komodo, or was actually signed by IdenTrust. And I trust IdenTrust and Komodo as companies. And since they issued this certificate, then I can in turn believe the certificate, right? And that all works to form what's called the chain of trust. So this root certificate, or the root CAs, these are the certificates that are from the certificate authorities that come pre-installed in your laptop or all your software, right? So what might happen is, let's say two servers are trying to communicate with each other. So they exchange certificates, and they're going to exchange what's called entity certificates. And that's going to have, hey, I'm, Broadcom, and here's my public key, and I've got this certificate issued by this intermediate party. So whenever a server gets a certificate, they can say, okay, this is the key, this is who owns it, but I don't know you, who issued this certificate. And so it's going to say, okay, here's the issuer certificate. I'm going to go down a level and check everything about who issued this entity certificate. if I don't recognize what's in this certificate, I'll keep going down a level until I hit something I recognize. And in this case, the root CAs are all pre-installed on my laptop. So I can say, oh, hey, I trust this guy. And as I trust the root, and the root trusts the intermediate, and then the intermediate trusts the end entity certificate by the transitive property, because I trust the root, therefore I can trust the end entity certificate. And so when you show me, or when the server presents this certificate to me as its ID, I now have reason to believe it's a real ID, and I can trust the ID, and now I know their key and who the key belongs to. So when I start doing this asymmetric cryptography to communicate with the server, I know I'm actually talking to who I think I'm talking to and not an imposter, right? So this chain of trust is really important, and that's how certificates are evaluated, and how software or people or whoever's looking at a certificate can determine, can I trust the information in this certificate or can I not trust it, right? So this all comes together to form what's called the public key infrastructure. And that's just the system of how the certificates, certificate authorities, and everything else comes together to form this whole hierarchies and chains of trusts where we can share identities with certificates and have them be trusted. Right? Just some miscellaneous kind of details that might be helpful for you, especially if you're trying to administer these in your system. You might hear the terms key store and trust store. A key store is, well, both of these things are repositories for certificates and keys. A key store is where you keep your self-identifying information. So if anybody asks you or your server to identify itself, it goes into its own key store. It's kind of like your own wallet. You pull out your own ID and you show it to whoever, right? So your key store is self-identifying information. And then your trust store is your repository of certificates or entities that you trust, right? So this would be all the certificate authorities. If you have other ones, you can add them into your trust store, right? So key store is to identify yourself, and trust store is to identify third parties who you trust. And then finally, you might work with self-signed certificates. In this case, this is when you're acting as your own certificate authority. So you at your company or at your job might generate your own root certificate and then sign certificates with your own root certificate. If you do this, you'll have to put that root certificate you generated in your own trust store, just so the trust works out with everything you're doing. But this is only advised for kind of testing in-house or just setting something up that's not going to be facing the whole world, because most people won't trust a certificate that's not from a certificate authority. So if you're going to be using certificates with people outside of your company, you'll want to get one issued by a real certificate authority, just so it's more trustworthy, right? So that's the conclusion of part one about the basics of certificates, kind of the stuff that goes on underneath and how they all work together to be able to identify servers or people digitally. So before I hand it over to Jameson, are there any questions kind of about the basics here?
There's no questions coming in the chat.
No questions. All right, I hand it over to Jameson.
All right, hello everyone. I'll introduce myself again because we don't have video, so that everyone knows my voice. I'm Jameson Walker. I work on the ACF2 security team, and I'm going to talk about digital certificates on zOS. This is part 2 of this presentation, not part 2 of digital certificates on zOS, just to clarify for this slide. So far, we've covered cryptography. We've talked about a PKI and how that fits in with cryptography. And then we've talked about a real world use case of why a PKI is valuable and why we use cryptography. I'd like to move us back onto the mainframe here and talk about some zOS terminology that you will hear in this presentation and that you may find in documentation and in your work on zOS. I'd also like to talk about some zOS theory, why we do some of the things that we do. And then finally, I'm going to run through a zOS case study of securing a CCS Tomcat server on zOS with a DigiCert signed certificate. To clarify, this is a CA Common Services Tomcat server a vanilla Tomcat server will not have the ability to support ESM keyrings right out of the box. So that's going to be at the end of the presentation that we'll run through that case study. The zOS terminology that we're going to talk about is ESM Certificate Repositories, Certificate Control, ICSF, Keyrings, Virtual Keyrings, and Special Users. So jumping right in, ESM Certificate Repositories. An ESM can store digital certificates and restrict access to them using the already familiar paradigm of resource rules. Well, these will be familiar to your security officers, hopefully. So RACF stores these rules in the RACF database, ACF2 in the ACF2 info storage database, and then Top Secret leverages the security file database. Essentially what happens here is that an application will ask SAF for a certificate via an RDataLib call. This is like an API call. And then if allowed by the ESM, the certificate data will be returned to the requesting application. Certificates can also be stored in zOS in the USS file structures as key stores and trust stores, like Seamus mentioned. However, there's a lot of shortcomings to this. If you care to know what some of those are, I can explain in the Q&A time. This brings us on to certificate control. There are two main ways to control access to certificates. There's the general control, which is defined by the facility IR DigiCert resources. These are universal access none by default. So no, once you instantiate these resources, you will not be allowed access to them on most ESMs. And then what you could go and do is permit server started task IDs to the required resources or individual users, stuff like that. There's also granular control. This is a little bit of a newer concept on zOS, but or in the ESMs, but a lot of places are shifting over to use it more and more. Essentially, you define our RDataLib, IRRAC DigiCert granular. This can get really complicated, so I'm not going to go over it in the examples today, but all of the ESM documentation has great documentation about how to set these up and administer them. But essentially, granular control can allow you to enforce naming conventions on certificates and keyrings, and it can also separate the administration access from the actual use access of certificates. So I could build keyrings and allow other people access to them without myself being allowed to read the private keys of certificates. This brings us on to ICSF, which is the Integrated Cryptographic Service Facility. This provides a lot of power to zOS users. ICSF is a software component for zOS that, in conjunction with hardware cryptographic features and an ESM, say RACF, can provide high-speed cryptographic services. What services can it provide? Well, it provides added security. It can store your private keys and hardware. It also provides private key encryption, so your private keys will be encrypted by a master key. It allows you to leverage the hardware cryptographic coprocessor. This is specialized silicon that is very quick at doing encryption, decryption, hashing, cryptography specific processes. It's also tamper resistant. So if someone tries to access the data on the cryptographic coprocessor via mechanical means, the chip will detect that and wipe itself. When you use ICSF, you also gain access to protect CSF keys and CSF serve classes. This brings us on to zOS keyrings. I think zOS keyrings are probably one of the most common and misunderstood concepts in zOS digital certificates. A keyring is simply a collection of digital certificates associated with a server or client task user ID. So what happens here is that a keyring is owned by a user ID. their keyring. And then you connect certificates to the keyring. You will then point a task to a keyring via its parameter file. And what will happen is the application will make an RDataLib call or similar to retrieve certificates, will retrieve the keyring, which returns all of the certificates on that keyring that the user making the call has access to that are connected to that keyring. When you add certificates, when you connect certificates to a keyring, there are two ways you can do this. You can use the personal usage, which allows access to public and private key of a certificate, or you can use certauth, which just returns the public key. There are also two types of keyrings. There's the explicitly defined keyring, which is what I just described. And then there's a virtual keyring, which is more of a concept than an actual keyring that you place stuff onto. So a virtual keyring is actually the set of all certauth or sitecert certificates. I'll cover site and certauth in a second. But what happens with a virtual keyring is when you specify it in a parameter file, you'll get back all non-expired certauth and sitecert certificates. This can be useful for servers where you want to limit who can access the server, or you want to be able to recognize all sorts of certificates connecting to a server, something like that, without having to create your own keyring and place all of these certauth certificates onto it. But what is certauth and sitecert? Well, these are special users. These are people who can own certificates. You can't log into your system with certauth or sitecert unless, I guess, you create another user to do that with that same name. But certauth is a special user that will own all certificates that complete a chain of trust. So say that you use DigiCert and I don't know, a bunch of other certificate authorities, and you have signing chains for all those certificate authorities, and many people across the organization use those certificate authorities and need access to the signing chains. You will add the signing chains onto the certauth user so that anyone can access those public keys without having to import their own copy into the ESM database. Site works similarly, but it can also be used if you want to share private keys between started tasks and stuff like that. We see sitecert being used less frequently than certauth. And then also regular users can own certificates. So a started task ID for a server could own certificates, or just me, Joe Schmo, could own certificates for my own use. This brings me to the zOS case study. So I have a CCS Tomcat server running on zOS, and I would like to secure it, secure connections to it. I would like to secure these connections via HTTPS. I would like to have access to administer these certificates within the ESM. I need to give my Tomcat server ID access to the certificates that it needs. I would like my certificates to be signed by a CA, in this case DigiCert. And just for clarification, that's CA, a certificate authority, not computer associates. I would like to store this server certificate in the ESM database. And I would also like to leverage digital keyrings. Oops. All right, so starting off with access. Let's just say I'm a security administrator on the system, so I can essentially do whatever I want. But if I wanted to give someone else permission to specifically administer certificates using general control, I would need to grant control access to the following facilities. These are all IR Dig T Cert facilities. So we would get access to add ring, connect, GenCert, GenRec, and then list and list ring. These last two are not required to administer the certificates and keyrings, but if we wanted to check our work, we would need access to them. Next, we need to set up our Tomcat user to have access to the certificates that it will need. This is pretty straightforward because the user, in this case ShareServe, will own the certificates. He simply needs read access to IR DigiCert list ring. If he were trying to access certificates that were owned by a different user, he would need additional access, either update or control access to this facility. All right, so now I'd like to secure the connection. In order to do that, I need a server certificate. It must be accessible to the server. Its private key must be secured, otherwise it will be without value to us. And it should also be publicly recognized. So we've already made sure that any certificate that we add to the ShareServe user and his keyrings will be accessible to the ShareServe user. We will keep this private key secure by adding this certificate to the ESM database. In order to make sure our certificate is publicly recognized, we'll get it signed by DigiCert. And then on the right here, we have a diagram that Seamus showed. And essentially in this diagram, our server certificate is the end entity certificate. And then the intermediate and root will be provided by DigiCert when we get our certificate signed. So this brings us to the commands we'll actually run inside of zOS. We'll get to a ready prompt. These are just screenshots because technology never cooperates when you need it to. So if I tried to do this live, I know I would lose connection or something like that. All right, so inside of the ready prompt, we're going to do these examples in ACF2, but if you use RecF or top secret at the end of this presentation, the slides which are provided, there's the exact same example for both the other ESMs as well. So the first step in ACF2, we're going to create a placeholder certificate. To do this, we're going to go into the profile user div cert data, and we're going to do a gen cert. We supply a label for the certificate, in this case, shareserve.server. We're going to supply subject information. This is a common name, so a name to identify the server, shareserve or share.org. Location information that's not strictly required. An expiration date, which is actually rapidly approaching here, and a label for our certificate. Finally, we can supply a size for the key. 2048 is plenty large for our needs. If you're using this in a production environment, you may also want to supply an alt name that contains the IP address or host name of the server. Once you run that command, ACF2 will generate a certificate into its database conforming to the information you supplied. Now that we have that certificate, we need to create a CSR, a certificate signing request. We will do this with the genrec command. We will supply the certificate identifier we created in the previous step, so shareserve.server, and then we will supply a data set name for our signing request to be placed into. This data set should not exist. ACF2 will allocate it for you. Once we have run that command, we'll have our CSR at this location, and we can FTP it off of the system to our local machine in the ASCII transfer format. It is important to note here that all of the things that make your certificate unique, its private key essentially, do not leave the ESM database. Inside of the CSR, there is the subject information, there is label information, public key, stuff like that, that it's okay if that information is publicly known. In fact, your certificate's more valuable if that information is publicly known, but your private key, the critical piece, stays secure in the ESM database. Once we have the CSR on our machine, we can go over to DigiCert and we can request that they sign this certificate. We'll upload our CSR, pay probably a lot of money to them, and wait. Once they have signed our certificate, they will send us an email containing the signed certificate and the signing chain for that certificate. This may be one file with multiple certificates inside of it, or it may be multiple files. Essentially, we will take those files FTP them up to zOS, once again using the ASCII transfer format. Once we have that information in data sets on zOS, we will move back into ACF2. We'd like to replace the placeholder certificate with the DigiCert signed certificate. To do this, we will use an insert command. Once again, we're in the user div cert data in ACF2. We will provide the same identifier we used in the first two steps. We will supply the data set containing our now signed certificate from DigiCert. And then we'll supply a label. This is the same label we used in the first step. I'm also adding trust here at the end. This tells the ESM database that we can trust this certificate. The ESM database, or the ESM, will automatically assign a trust status to certificates based on whether it can complete the chain of trust or not, and a couple of other factors. When we run this command, it combines our private key information in the ESM database with the signed certificate information from DigiCert. So then in the database, we now have a signed certificate with our private key connected to it. Additionally, we will need to import the signing chain. Depending on the way that the certificate is packaged when it comes back from your CA, the ESM may import this information automatically during this first insert, or you may have to do it manually. Notice we're doing an insert command again, but this time we are adding a certificate with the identifier certauth.root001. This certauth is this special user that I described earlier. And then root001 is just a unique name for this particular certificate authority certificate. We supply the data set containing the certificate and a label, and once again, the trust status. We're putting the certificate on the certauth user so that other users will have access to the certificate, so that they can check their signing chain as well without having to import this certificate multiple times into the database. If this certificate already exists in the database, ACF2 will say, hey, look, this certificate already exists. I don't need to import it again, and it'll give you an error or a warning. So now that we have our certificates in the database, Now that we have our certificates in the database, we are going to create a digital keyring that we can provide to Tomcat so that he can find the certificates. It also helps us to keep track of what certificates are associated with what users and tasks. To do this in ACF2, we'll go into the profile user div keyring. We'll run an insert command and supply an identifier for our keyring. This will be on the share serve user, and the keyring will have a identifier tomring and a ring name of tomring. Once we run that command, ACF2 will create a certificate keyring in the database. We can then connect certificates to it. We will use the connect command to do this. We'll supply cert data, which is the identifier for the certificate we would like to connect. We'll supply keyring, which is the shareserve.tomring that we just created in the first step. And then we will supply usage. In this case, because the cert data that we are supplying was our server certificate, we want to use usage personal, because when this keyring is retrieved, we would like to receive both the public and private key of this certificate. Running this command will connect the certificate to our keyring. We can then move on to the signing chain. In this case, it's just one certificate for us. So we'll run another connect command, once again, supplying cert data. In this case, the certificate's owned by certauth, so we're going to supply certauth, and it is identified by root001. We are connecting it to the share serve tomring keyring, and the usage will be certauth. When we get this keyring, we would only like to receive the public key of the certificate, which is good because we only have the public key of this certificate. If you run an in-house certificate authority, you may have the private keys for the signing chain in the database, but in most cases, you will not need to or want to retrieve those when you're just using the certificates to complete a chain of trust. All right, that's the last step. Then you'd flip back to your Tomcat configuration. You would supply this share serve.tomring keyring to that task and tell it you want to run with HTTPS or in secure mode, something like that. Restart the server, and you'd be able to connect via HTTPS on an encrypted connection. That brings me to the end of the slides that I have. I think we have plenty of time for questions. And I would also like to remind everyone to please do your feedback. This session is 5 Baker Delta. And also please donate to the GSE charity for this year.
So have we got any questions? If you've got any questions, please put them in the chat. Can you see the question?
Yeah. All right, Damien, I see a question here from Damien. Can you please explain cert auth versus site auth? So I will flip back to the slide here. I know it does not have a ton of information on it. I link in the later in the presentation, if you download it, out to the doc for ACF2 RACF and Top Secret, which explains these users a little bit more. But essentially what's going on here is you have 2 different locations to insert shared certificates. So the cert auth would be a user that will own all of the certificates to complete a chain of trust. In that diagram that Seamus had, here, I think I'm covering it with the comment box here and webcam. So the end entity certificates would go on individual users, and all of these intermediate certificates and root certificates would go on the cert auth user. That way anyone could go out and retrieve the public key of those certificates from the cert auth user without having immense resource access in the system. Now, site auth is a little bit different, and I think this is less commonly used, but site auth is set up for as a place to store certificates or user to own certificates for web servers, places that might share private keys and signing certificates. So if you had 2 Tomcat servers running under 2 different IDs, but you wanted to use the same certificate for both of those servers, the same end entity server certificate for both of those servers, you could add that certificate to the site auth user and allow both of the Tomcat users access to read private keys from site auth, or actually it won't be site auth, it will be either site or site cert, depending on the ESM. And this is just, once again, giving you a common place to put certificates that are shared between users. There's also a use case. Say you had people connecting via FTP to your system and you wanted to ensure that you knew the people who were connecting. If the individuals were connecting with a certificate instead of a username and password, you could put the public keys of those users onto site auth and make those certificates, that virtual keyring, available to your server, so they could identify the individuals connecting and make sure that they are who they say they are. And then, that's pretty much the extent of those 2 users, if that makes sense. I'll put this slide up again so everyone can scan it if they need to. Or once again, we've uploaded these slides to the presentation portal. So whenever those are available, I'm assuming they'll be available with the recordings. You can take a look and see the additional resources and stuff that we have at the end here.
Yeah, this should be available tomorrow at the latest.
Okay, perfect.
Any more questions? Okay, thanks very much,
Thanks
Jameson and
everybody.
Seamus.